We present a hierarchical control framework that enables wheeled bipedal robots to perform mobile pedipulation for planar object sliding using their wheeled legs. With this framework, the robot can simultaneously maintain balance and regulate contact forces, enabling coordinated locomotion and pedipulation behaviors. To capture the 3D dynamics of wheeled bipedal robots, we introduce a reduced-order 3 rigid bodies, or TRB model. The model represents the torso and 2 wheels as floating rigid bodies, while retaining the hip roll degree of freedom and supporting multiple contact modes. The control system is organized hierarchically. A robot object motion planner generates reference trajectories, incorporating stick-slip transitions. A TRB-based nonlinear MPC tracks the desired state references and contact forces. Finally, a whole-body controller converts the commands into joint torques for accurate hardware execution. We first validate our framework in simulation through locomotion tasks, including forward and backward driving, in-place spinning, torso height, pitch and roll control, as well as combined motions involving simultaneous linear and angular velocities. Stepping motions are also validated in simulation, demonstrating effective handling of swing phase wheel dynamics. For object sliding tasks, the robot performs a lateral sliding experiment by stably pushing away or retrieving an object in the lateral direction while maintaining contact with the object using one wheel. We also propose another pedipulation motion, termed scooting, in which the robot dynamically applies large longitudinal forces to initiate the sliding of relatively heavier objects on low-friction surfaces. We evaluate object tracking in lateral sliding simulations with unknown object mass. Compared with the TRB-based controller, the unified TRB object controller achieves lower tracking error and better robustness. In hardware experiments, the robot first tracks velocity commands from a human-operated joystick to perform locomotion tasks, including rapid in-place spinning, weaving around 2 cones, and accelerating forward. Scooting motions are also demonstrated on the hardware platform, where the robot slides a 4-kilogram object over a total displacement of 0.228 meters through 8 scooting cycles. The NMPC regulates the ground reaction forces to accelerate the robot, then generate a large horizontal force to initiate object sliding, and finally re-establish balance after sliding. We also conduct an under-desk retrieval task, in which the robot steps onto the object and retrieves it via lateral sliding, highlighting the potential of wheeled bipedal robots for non-prehensile manipulation in constrained environments.